Hi, welcome to the demonstration of topic modeling. So I just cloned the repository from GitHub, which is mentioned in the report. And so let's go and open the GUI for topic modeling. It takes some time to import all the libraries and load the GUI. So before that, I just want to say this file is added. It's not present in the um, repository. This has to be manually added because of the size limitations of GitHub. So yeah, so our GUI is loaded. So for the demo purpose, we just use an existing model that is already created. So you can see all the files that are there for the model are present in here. But you can also choose the different number of topics, but you have to do a create model first. So in this case, I just do a load existing model. And I have loaded all the files for that particular topic. Now I go and search for a particular author. Okay, so we can see the results here. So we searched for M Jordan. So it didn't find the exact name of M Jordan, but it found a similar name, which is Michael I Jordan. This is done by using Python's diffleap package and then the get closest match function. These are the document IDs that are published by the author. And then we can find the similar authors if you want to recommend him some other authors based on the topic distribution of the author. So this is computed by the measuring the Hellinger distance between two probabilities. It's because Euclidean distance doesn't make sense to compare the closeness between a probability distribution. So you can obviously say that he himself is the top, and then these are the recommendations we'll use for him to have a similar others. Next, we can see year by year how the topics have been progressed for him. So there is no he didn't publish any papers in 1987 and 1988, and after that he won he published for around 12 years. And so we can find for the years he published in the topics in this year, the topic distributions. So this is the topic distribution, more like topic score, not topic distribution, because it's like a sum of the topic probabilities of all the documents he published in that year. So this gives for every year, and then we can also find um, the dominant topics he worked on. So it's like you find the cumulative sum of all the topic distributions over every year, and you find the dominating topic in each year. So that tells you uh, what is his most uh, dominant topic over a period of time. So I can see all this period topic 5 has been his most dominant topic, and then he switched to topic 1 in 1999. This only gets topic switching only happens when the combined cumulative probability distribution exceeds the previous one, so which happens in this case in 1999. um, Next we can go and search for some query image recognition and see so it just tells you what are the topics it kind of belongs to. But we didn't get nice good results. Maybe it's some words optimization. So it kind of gives you whatever the topic it belongs to more in general in here, and then the top keywords of the topic. Next we can find the year. We can type any year and then we can ask for the uh, top topics of that particular year. So in 1993, obviously topic 3 is more dominant, and then we can find the what topic 3 represents in here, what are the top keywords in the topic. So it's more like about neural networks and yeah, some signal processing things like response neural activity stuff. Then we can also choose like a particular topic and then look for like how topic got evolved over that time, over the period of time. So this gives you the topic 1 score for all years. So you can see like over years the words in the topic 1 has evolved quite good, and then these are the top words of the topic 1. And so we can also look like, instead of plotting for only one particular thing, we can also look like all topic evaluations. So which gives you for all the 9 topics in this case the evolution plots for all the over all the years. Next we can look like what are the top titles of topics. So we find the documents where the topic distribution is maximum, and then we try to print the top 3 titles for that particular topic. So you can see like for the topic 0, these are the top titles. Like these titles have more topic 0 distribution, or the highest topic 0 distribution, and these are for the topic 1 and topic 2. So we can kind of estimate like what are the topics, what these documents are all about. Like for example, in this case we can see like this topic is about topic models. Yeah. And then we can also search for document id. Let's say like get document info. This gives you like what are the topic distributions, and then what are the most similar documents to that particular topic. In this case, like the id with 13 is the most similar one, and it says about like patterns and neural networks. You can see again like this has neural networks and then patterns. Yeah, more like. And we can also view the other clustering, like we can do the clustering from the topic distributions of others. And so in this case, like this is like reduced to 2 dimensions for better visualization and using t-SNE. And then yeah, so here the radius represents how many documents author published. Suppose you can look here like this author has, Michael I. Jordan, published the largest number of papers, which is 79. So you can see again this is inside this. So like I mean so you can see this part again consists of both these guys. Like so the larger is the radius, the more is the authors published, and then the center actually represents how close or similar the authors are. So this is like a clustering plot, but the size of the point is like the radius of a point is depends on the number of documents published by the author. Then we can also look like what other topics are mostly like. Again we have 9 topics in other topic model, and then these are the top words of each topic. Similarly, we can also do document clustering from here. Similarly, we can also do document clustering from the document topic distributions, which again gives you this plot. Again, these are reduced in dimensions, and then using tsne, so you can see like there are some good clusters, and then the points we can see like there some points are far, because like it's reduced to 2 dimensions, but if we can able to view in higher dimensional space, they'll probably be closer because of the cluster. So then we have like, so how do we choose the right number of clusters? In this case we choose 9, and the reason is mainly because of this. So we do a clustering of all the things that are available, like over multiple number of clusters, and we can see like the new point is around 9, which is also like the number of topics we used. Similarly for other clustering. So this just tells us there is a strong correlation between the topic distributions and then the clusters, or like mostly each document is majorly consists of one particular topic. So again, the other clustering is done, and then it also again gives you around 9. So yeah, and then after this, like we used a oh sorry, the other clustering is done now. Yeah, but again still again good at 9. There is some problem with GUI in reporting the classification thing, but we also like created a classification problem on top of this. Like we have the topic distributions and we have the cluster labels. So we created a classification problem to see like how good the fit is. So if you have like a random distributions on topics, so it will just give a bad clustering, and thereby like if you do classification problem, it gives you a low accuracy thing. So so to evaluate how good our fit is, we made a classification problem, and then you can look in here, the accuracy is pretty high, around 99% for training and the 98% for testing, for the top number of chosen number of topics of 9. So also the accuracy drops as the number of topics increases, but this is also because like we are trying to fit documents into one particular topic, where even when there is increasing number of topics, so when the topics are increased, it's just like each document can have like the topic distribution increases for each topic, and forcing them into one particular class or cluster is not reasonable, and so we can expect the accuracy to drop over time. But this above 90% accuracy tells us that it's a good measure of the things. Okay, I think that's the end of this demo. Thank you.